한조가 제일 안 좋아. 진짜. 한조가 스나보다 좋은데. 이도는 공 안 맞잖아. 아무도. 이도는 계속 보고 나중에. 깼다고. 스나는 한조는 화살이가 느리잖아. 보고 피하는. 안 맞잖아. 뒤에서 시작하시고.
Okay, let's start. Yeah, so today we start learning about this eigenvalues and eigenvector. So it's almost like the final king of this linear algebra. 이거 선형대수의 끝판왕격에 해당이 되는. So yeah, this is very important, and so it's used in many different applications. So it's very useful to know. Okay, so I'm not sure if you checked out this cartoon, but it's 본 사람 있어요? 이거 어떻게 키우나? Okay, I cannot expand the. Let's see. Okay. Okay, so yeah, if you check out this cartoon, and then it's about some geeky story about the math. So there is a king of a derivative or differentiation and integral and so on. So in this case, 네, 이거를 So you guys know this kind of operator, which is performing the differentiation with respect to this x, right? So in this case, if our function is x squared, and then you know it's 2x, right? So in the cartoon, this is described as a kind of a king of differentiation. So if you keep applying this onto our function, and then, so suppose we perform this again, and then this becomes a constant, and then once we do it again, and then it will eventually become 0. So it's like gradually killing this guy, right? But in this case, so this was living in a particular kingdom, and then there is another, like a savior for this kingdom, because this guy kept killing all the people in this polynomial world. And some kind of this guy, so this is our savior, and then in this case, even after we take the derivative of it, it will remain the same. which means even if we keep applying this differentiation operator, this guy will still be alive. Okay? So that was part of this cartoon. Okay. So this eigenvalue and eigenvector has a little bit of a resemblance with this guy. So in that case, the operator, like this guy, the differentiation operator in this cartoon corresponds to the multiplication with the matrix A that we are handling. And then the savior is some kind of a vector x, okay, but that is our savior, so it should be some kind of a special vector, okay. And then how this guy survive after this multiplication is through changing this guy into some constant. So it's not about like whether it's dying out or survive, but it's about changing multiplication with the matrix A into much easier form. So suppose this guy, this bad guy, which corresponds to the multiplication with the A. Let's think about like multiplying A like 100 times and x. Okay. In this case, it means, so we first multiply A times x, and then this will give us a vector, and then we keep multiplying A again, and then like this. Okay. So altogether, we are multiplying A 100 times, and then vector x. Okay. So in this case, so if I'm going to ask you to compute this guy, and then I'm going to give you A as 1, 2, 3, 4, 5, 6, 7, 8, 9. And then vector x will be like 2, 1, 0, for example. So I'm going to give you this A and x. And then you'll have to multiply this A 100 times and then multiply x, or you keep multiplying this guy with the x like 100 times. Okay, so it's a really time-consuming process, right? So it would be really annoying process. Okay, but in this case, for so if someone gave the vector x as a kind of special savior, okay, and that vector, so suppose this vector x. So this should be some kind of special vector. So it cannot be any vector. It's determined in a particular way by your matrix A. Okay, and so this lambda is just a constant. Okay, so this is a matrix, and this is x is a vector, and lambda is just a constant, and then this is the same vector x. Okay, and then let's say lambda is 3, and it's a 3x. Okay, so in this case, so let's keep multiplying A with the x. So in the case of an ax, it will become 3x. So from this conversion or this relationship, you'd have to multiply this entire matrix with the vector, which involves a lot of computation. But what about this? 3 times x. In that case, we can simply perform the scalar multiplication with each element, 2, 1, 0. So for example, like 6, 3, 0. Right? So it's much easier. And then let's consider this a to the power of 100 times x. In this case, so it will become a to the power of 99 times ax, right? And then this guy, we know this guy is just a 3x, right? And then what about this? 8 to the power of 98 times 8 times, yeah, so 8 times 3x, but let's move this guy to the left, okay? So we can do that, right? So we can move this scalar multiple into the far left, and in this case 3 times 8 to the power of 9 is 8, and then it's also becoming 3x, right? So for 1a we can change it to just a scalar multiple of 3. So with the multiplication of a 100 times, and then it will become 3 to the power of 10, right? And then x. So simply, instead of having to compute all these tedious or time-consuming matrix vector multiplication, that will become really simple as this form. And this is still a scalar multiplication with the vector x. So the result will be 3 to the power of 10 times 2, 3 to the power of 10 times 1, and 0, right? Okay, so this is actually related to the eigenvalue and eigenvector that we will learn in this chapter. Okay, and the reason for computing the eigenvalue and eigenvector is because we want to simplify this kind of thing in a much easier form. Okay, so instead of having to perform many multiplications of many of the matrix multiplication into just a simple scalar multiplication. Okay, so that is the main beauty of this eigenvalue and eigenvector. Okay, but other than this kind of eigenvector thing is really widely used. So for example, if you search for a certain keyword in a Google, and then you perform just a Google search, and then you will get a ranked result of the web pages, right? So how Google rank these pages is completely based on this eigenvector or eigenvalue things, okay? And the algorithm to perform what should be the top one that we see from the search result is completely determined by this algorithm. You just keep multiplying some matrix onto some vector. So in that case, this kind of eigenvalue and eigenvector can be really helpful. Okay? Okay, so here the point is given a matrix A, okay, so our task is to find our savior matrix, our savior vector x and the corresponding lambda, right? So as I mentioned, every vector for x does not satisfy this guy. So you just pick up an arbitrary vector like 2, 4, 6, and then you just plug this in, and then usually, so given A in this form, for example, okay, in this case, if you select this vector x just arbitrarily like this, and then it will never satisfy this. So you can never obtain such kind of lambda to satisfy this kind of equation. Okay, so there exists a special vector x that can satisfy this equation. Okay, and then corresponding lambda can be obtained if the vector x can satisfy this kind of equation. Okay, so in this chapter, basically what we will learn is to how to obtain this vector x and lambda. Okay, and also let's think about this a little bit of a geometrically. Okay, so let's make it simple, like a 1, 2, 3, 4, and then 2, 1. Yep, 2, 1. Then what is the result? What is the result? It's 4, 10, right? So in this case, let's think about their geometric kind of a conversion or transformation. So it's like the 2D space x comma y, and then it's a 2 comma 1. So originally the point was here. So our input vector is this guy, right? And then this became this vector. So okay. So in this case, so this was our input vector x, and this was our output vector y after multiplying this matrix A. Okay. So in this case, this linear transformation changes the length of the vector and also the direction of the vector or angle of the vector. And that's kind of obvious thing, right? So a vector is composed of two information or two parts. One is magnitude or length of the vector, and the other is about the direction of the vector, right? So that is two information that forms one particular vector. And then after multiplying some matrix, after multiplying a particular matrix with that vector, the resulting vector will have a different direction and also different length, right? That's quite obvious part, right? But what about this? So suppose given this matrix A and given this matrix, given this vector x, that is our savior vector or special vector, and that in that case lambda was 3, and then it will be like this, and then it will be having the result of 6 times 3. So 6 times 3 is 6 times 3. So the resulting vector is this guy, right? So as we see from this scalar multiplication with the original vector, we can see that the direction does not change in this transformation. Only the magnitude changes. What is that magnitude? The ratio becomes this eigenvalue or this lambda value. So it's basically changing only the length of the vector 3 times larger than the original length. But it doesn't change any directions. Okay? So that is kind of a beauty. So for this special vector, even if we multiply matrix over and over, the given matrix A, so we keep multiplying A over and over, but the resulting vector will only change in terms of its length, but its direction will not change at all. Okay? And also, yeah, as we will see, like in chapter 5.3, so it's called, yeah, this kind of thing is related to something called diagonalization. Diagonalization means, so in this case, let's see, 3 times this vector, we can represent it as matrix times vector multiplication. So for example, like this, okay? So that scalar multiplication with the vector can be also written as matrix times vector, but that matrix is just a diagonal matrix, okay? So in that case, if you compute the result, it will be exactly the same as this guy, okay? So it can be thought of kind of, yeah, so instead of multiplying really like complicated matrices where all the elements are filled up with the non-zero values. So we see all non-zeros all over in the different elements or positions, right? But instead of having to multiply this, we are now multiplying this much simpler matrix where we have only the diagonal entries in our matrix. Okay, in that case, the computation becomes really simple. Okay, and that computation is just an element-wise multiplication with this guy and this guy. Okay. Okay, so and then let's generalize a little bit more about this diagonal matrix multiplication. So it is like 5 times 3 and 0, 0, and then 2, 1, and then it will be like 5 times 2 and 3 times 1, right? So these are just scaling the diagonal, the vector elements by using each of these diagonal entries. Okay. Yeah, so this is a kind of intuitive understanding or some kind of a how we understand this eigenvalue and eigenvectors. And then, so if you remember some coordinate vector. So what was the coordinate vector? So coordinate vector was 1, 2, 3, 4. And then I'm gonna give you let's use 1, 2, 3, 4, 5, 6. And then I will give you 1, 2, 3. So this is a vector x, and this is our matrix A. But let's consider that as a basis that has these two basis vectors. So let's call that as B, meaning it's a basis. And then, how did we compute this guy? B coordinates of A. B coordinates of A. So what was the meaning of it? What was the meaning of it? So although it's in a 3-dimensional space, but I'm gonna just describe it as a 2-dimensional space. So we have a point here, so that is 1, 2, 3, and then our two of the basis vectors. Suppose that was something like this. So this guy was V1, and this guy was V2. Okay, and then so first of all, what will be the dimension of this B coordinates of A, X? Is it 2-dimensional or 3-dimensional? It's 2-dimensional, right? Why should that be 2-dimensional? So basically what we are doing here is that, so suppose that was C1 and C2. And then what we are trying to do, the C1 and C2 that we are trying to obtain comes from here. X should be represented as a linear combination of C1 and C2, the V1 and V2 with the linear combination coefficient of C1 and C2. And that C1 and C2 will form your coordinate vector with respect to this basis B. Okay? So in this case, geometrically, that means, in this case, so if you remember it, this guy, what is the coordinate vector of this? What is the coordinate vector of this? So I'm gonna give you this vector as x, okay, and then what will be the coordinate of it with respect to the basis b? It's a 1, 1, right? Because it's composed of the summation of, from this parallelogram, it's adding 1 times v1 and 1 times v2. So these linear combination coefficients should be 1, 1, and 1. Okay? So in this case, given this guy, so it's like 1.2 v1 and it's 1.5 v2. In this case, C1 will be 1.2, C2 will be 1.5. Okay? So that was the meaning or interpretation of this coordinate vector with respect to the basis B, right? Okay, and then let's consider, so let's remember how we obtain the C1 and C2. So how would you obtain the C1 and C2? So although in this figure I gave you just this 1.2 and 1.5 as just an example, but in order to compute these two values exactly, we have to solve this guy. So this is a B. So B times, so let's call this vector as C. So B is this matrix. So B is this matrix. So B times C. Okay, C1 and C2 should be this vector that we are given, X, right? 1, 2, 3. So we have to solve this guy, right? But in the case of an eigenvectors, so let's see. So suppose your matrix A has like two vectors, v1 and v2, okay, and then suppose it happens that this eigenvector, v1 and v2, which is your basis vector that spans this column space of A, that vector happens to be the eigenvector as well. So in this case, in the case of v1, it satisfies this, and in this particular case, lambda 1 was like 2 v1. Okay, and then v2 is lambda v2, lambda 2 v2, and in this case, lambda was, for example, -1, for example. Okay, let's make it 3. Okay, so your basis vectors happen to be also the eigenvectors that satisfies this kind of equation. Okay, and in this case, I'm gonna give you like some vector 1, 2, 3, which is x that we saw in the previous example, like this. In this case, suppose you obtained the coordinate vector, so x, let's call that as b, and b1 and b2, and let's consider this coordinate vector. That was like 3, 5, and then it means x is represented as this, of course, right? So so your vector x, you obtain this kind of coordinates with respect to your basis vector. It's exactly the same as what we learned, right? But in this case, in this particular case, we are assuming this basis vectors are, this is v1 and v2. So these are also the eigenvectors, okay? So they are not just the basis vectors, so they are basis vectors, of course, but they additionally satisfies these equations, okay? Eigenvector and eigenvalue equations, okay? In that case, once you obtain this, once you obtain the vector x in this form, and then we are also doing the exact same task of keeping multiplying this matrix A. In that case, let's see how this representation changes. So in this case, it will be A times 3 V1 and 5 V2, right? And in this case, 3 times A V1 plus 5 times A V2, right? In this case, A V1 changes to 2 V1, right? So 3 times 2 V1 plus 5 times 3 V2. So this was lambda 1 and this was lambda 2, because A V1 equals lambda 1 V1, okay? A V2 becomes lambda 2 V2, okay? And then let's also multiply A again. In this case, we can plug this guy in, right? 3 times 2v1 plus 5 times 3v2. Okay, so you know what I'm gonna do in this step, which is similar to what we saw in the previous page. So in this case, 3 times 2 times A v1 plus 5 times 3 times A v2, and then this will become also 2v1, and this guy will become 3v2, right? And so it's 3 times 2 squared times v1 plus 5 times 3 squared v2. Okay? And what about this? A to the power of 100 and x. Can anyone give an answer for this? Yeah? Yeah, can you speak louder? 뭐죠? 3 times like this, right? Times v1 plus 5 times what? v2, right? Okay, so so this is this is the result. Okay, so here in this example, the main difference of this example from, where is it? Yeah, this guy. Okay, in this case, we started, our starting situation was that the vector x in this AX, vector x was assumed to be the eigenvector. Okay, so that was really special case because there are only like a few eigenvectors, right? But what if our vector x is just an arbitrary vector? Okay, in that case, that arbitrary vector can be represented in terms of the eigenvectors. Okay, so this was just any vector, but we now represented it as linear combinations of the eigenvectors that the matrix A has. And in that case, A to the power of 100 times x can be really, simplified as well in the exact same way in this form. Okay, it's just still linear combinations of these eigenvectors, and eigenvectors gives a really good thing of changing a matrix multiplication with scalar multiplication. 네, V1, V2가 아이겐벡터일 때. 아, 저거요? 찾아야 돼요.
V1, V2가 아이겐벡터가 아니면
아이겐벡터가 아니면 여기서 어디 갔어? 요 짓을 못하죠. 그죠? 요 짓을 못하니까 이건 성립이 더 이상 안 돼요. 그러니까 A를 상수로 싹 바꿔치기를 할 수가 없어요. 유일하냐고요? 네, 그게 또 우리가 배울 건데, So the student asked a question about how many eigenvectors do we have given a particular matrix A. So in this case, let's consider the requirement or condition of our matrix A. So first of all, is it possible that A is a rectangular matrix or A should be square matrix? So can A be rectangular matrix? Like this kind of a rectangular shape of a matrix A. Is it possible to satisfy this equation? So let's use the example like a 4 by 3. In this case, let's consider the size. So A should be 4 by 3, and V will be what? What is the size of V? It's a 3, right? In order to be able to define A times V, A should be three-dimensional vector, right? But what about the resulting vector from this equation? So that will give us 4-dimensional vector, right? Because A is 4 times 3. But what about this guy? Lambda is just a scalar, and V is still a 3-dimensional vector, and after doing the scalar multiplication, it will become just 3-dimensional vector, right? So this 4-dimensional vector and 3-dimensional vector should be the same, which is never possible, right? So in order to be able to satisfy this eigenvector equation, we are assuming the matrix A to be square matrix, because if A is rectangular matrix, the vector size, I mean the length of the vector of the left hand side and right hand side will become different, right? So here again, when talking about the eigenvector and eigenvalue, we are always assuming that A is square matrix. Okay, and then now we learned that A is square matrix. And then let's get back to the question that the student asked. So suppose our matrix is 4 by 4. 4 by 4. And in this case, the issue is how many eigenvectors are existing. And also how many eigenvalues are existing as well. So previously, in this eigenvector, eigenvalue equations, so we first considered eigenvector V, and then considered lambda, right? So we considered eigenvector first, I mean the vector V first, and then thought about the corresponding lambda, right? But in practice, when obtaining this eigenvalue and eigenvector, we first obtain this lambda. So it is something like this. So lambda is scalar, and V is a vector. So we have to solve for both things. So we have to obtain both of them. But between these two, obtaining lambda is much easier. I mean, obtaining lambda first is much easier. And then once you find the lambda, and then finding this eigenvector corresponding to this eigenvalue is is easy job. I mean, it can be done by just solving a linear system, specifically homogeneous linear system that we will see. And then back to this shape of matrix 4 by 4. In this case, in terms of the number of eigenvalues, the maximum possible number of eigenvalues will be 4. And then, consider this case where we have 4 different eigenvalues. Okay, so eigenvalues can be different. So in this case, so as I mentioned, suppose our bases are basis vectors are v1 and v2, and for each of these v1 and v2, they will have their own eigenvalues. So in this particular case, v1 had an eigenvalue of 2, and v2 was had the eigenvalue of 3, right? So eigenvalue can be different for different eigenvectors. Okay, so back to this question. So we have suppose we obtained 4 different eigenvalues, and then each of them can have eigenvectors. Okay, so in that case, one eigenvalue can have one eigenvalue at least has one eigenvector. Okay, so in that case, if we had 4 different eigenvalues, and it will at least have 4 different eigenvectors, because each one will give at least one eigenvector. Okay, but the total number of eigenvalues and the total number of eigenvectors that we collected, if we collect all the eigenvectors obtained from each of these eigenvalues, and then if we just collect all the eigenvectors, and then the total number of these eigenvectors are also bounded by 4. Okay, so in this case, you can easily think of it as having a maximum number of eigenvalues as 4, and also the maximum number of eigenvectors are also 4. Okay, so we will see why as we go through these chapters. Okay, so this is a kind of high-level overview about what we will learn in this chapter. So I think having this kind of insight is really important, because like obtaining eigenvalues and eigenvectors, they are a little bit of a tedious job, and you might have to perform some computations. But at least you should know why you are doing this kind of things. Okay, so back to this slide. Let's start with the definition of an eigenvector. So it's exactly what I mentioned. So eigenvector is satisfying this guy, where some scalar value lambda, and here the important part is this guy, non-zero vector x. Non-zero vector x. Although it's really trivial, but it's really important part. So our eigenvector should be non-zero vector. Okay, so what if our eigenvector is a 0 vector? So let's consider this case, A times x, where this vector x is just a 0 vector. It's just a completely 0 vector. And it will always generate just a 0 vector, regardless of what the matrix A is. Right? And then the lambda can be any value, because vector x is already a 0 vector. Right? So in this case, lambda, any real value can be our lambda. So we exclude this kind of trivial situation. Okay, so that way, from the beginning, we assume that the vector x, our eigenvector x that satisfies this equation is always non-zero vector. Okay, they have some direction and the length of the vector. Okay, so that is an important part. And in this equation, x is called eigenvector and lambda is called eigenvalue. Okay. And here, in this case, the vector x, which is an eigenvector, is called this eigenvector corresponding to lambda. Okay, so there is a correspondence. So as we saw in the previous example, a particular lambda comes together with particular eigenvector. So particular eigenvector and particular eigenvalue are a pair, okay, that satisfies this equation altogether. Okay, and then we can find another pair of eigenvector and eigenvalue that satisfies this equation. Okay, so that was some kind of this example. So we consider two different vectors, and each of the vector satisfies this, but with the different eigenvalues, right? So this guy is paired with the lambda 1, and this guy is paired with the lambda 2. Okay, so we can always think about this paired relationship between a particular lambda and its associated or corresponding eigenvector and eigenvalue pairs. Okay, so the next question, next equation is really important part as well. So let's start with this guy, ax equals lambda x. So in this case, we can manipulate this equation in this form. Lambda is a scalar, but we can just put the identity matrix I between lambda and x. So in this case, let's consider the shape of the matrix. So A is this kind of shape, and x is this, and that was something like this. So it was A and x, lambda and x. But in this case, we manipulate this guy so that we put the identity matrix here. So this is an identity matrix. And then our vector x. Okay? So that's a really simple manipulation. So A and x, lambda, x, lambda, I, and x. Okay? And in this case, we just move this part to the left hand side so that we obtain this guy, ax minus lambda I x. And then we can factor it out as a minus lambda I times x. In this case, it should be 0, right? So if we imagine, or if we consider the shape of this, so A was this, and lambda times I. So what is the lambda times I? Or what is this part? So this part is, so suppose lambda was 3, and the matrix size was 4 by 4. And then lambda I is just a 4, 4, 4, 4 on the diagonal, and 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? So this is a lambda I, right? And then A minus lambda I times x should be 0. So in this case, the matrix is this kind of matrix of 4 by 4, but the vector x becomes vector, 0 vector. Okay, so in this case, suppose, so let's change 4 as lambda, because I just I just use an example. So these one should be lambda because we don't know yet what the lambda is. And then matrix A is 4 by 4. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. I said the size of matrix too large. Okay, so this is a 4 by 4 matrix that we have. And then what should be this guy? What should this guy be? A minus lambda I. So this matrix has this form. 1 minus lambda, right? 6 minus lambda, 11 minus lambda, and 16 minus lambda, right? So this is basically subtracting this lambda from the diagonal entries from the original matrix A. So that is the meaning of this A minus lambda I, right? And anyways, we obtain this matrix, and let's call that matrix as B, which is A minus lambda I. And then B times X equals 0 is the same equation. And in this case, we can solve this vector X. And then in this case, can X be 0 vector? So the trivial solution or the obvious solution for this equation is when the vector x is all 0. But as I mentioned, we are excluding this kind of really simple case where the eigenvector x is a completely 0 vector, right? So we consider some non-zero eigenvector. So x should be non-zero vector, right? So what is x? X was the eigenvector satisfying this, and then we just simply manipulated this equation and then arrived this equation. And then this equation is a really familiar form to us because we are given a matrix B, and then we have to solve this non-zero vector x, right? So in this case, in order to have a non-zero vector x, what is the condition for the matrix B? So when is this equation? When does this equation have non-zero vectors for solution? Eh? Yeah. So in this case, it's a we call that as a homogeneous linear system. And then in this case, if B has linearly independent columns, which means B has no free variable, and then the vector x should always be only just a 0 vector. But if B has the columns of B, right? The columns of B are linearly dependent, and then we now have non-trivial solution or non-zero vector for this vector x. Okay. So in order to have some non-zero vector here as a solution, or in order to have some non-zero eigenvector here, our matrix B should be linearly dependent, right? And then how can we make this guy as non-linearly dependent? So originally matrix A was, for example, linearly independent. Okay, so suppose matrix A, before subtracting lambda on the diagonal, it was linearly, let's suppose it was just a linearly independent. Okay, and in that matrix, we just subtract this lambda from the diagonals, and then this matrix should now be linearly dependent. Okay, so that's when we can obtain this eigenvector or non-zero eigenvector, right? So basically, the task of finding this lambda or task of finding eigenvalue is that we want to find the we want to find the lambda so that this matrix B becomes linearly dependent. Okay. So that is kind of a meaning of it's kind of another meaning of eigenvalue, and also. Yeah, as I mentioned previously, like in this case. So we always consider the square matrix in this case, right? So we only think about the square matrix, and we exclude completely about this rectangular matrix. And then in case our matrix is a square, and then there was a theorem called this inverse matrix theorem, or IMT thing, right? So IMT is, so in case our matrix is a square, and then the matrix, if that square matrix is has a linearly dependent columns, and then it was the same as this matrix is not invariable, right? It was not invariable, right? And then also it was also the same thing as this kind of the columns of the matrix does not span the whole space, right? So that was another kind of meaning in case the matrix is a square matrix. Okay, so basically from this matrix, what we are doing here is that we want to find the lambda to make this matrix B non-invariable. Okay. Okay, so
네, 아까 그 아이젠 벡터 밸류 하나에 한 개 이상의 아이젠 벡터가 있어요.
네.
노트리뷰하면 무조건 아이젠
아, 예, 맞아요. 그거 맞고요. 네, 그거 맞아요. 맞는데 역시 이것도 베이시스 개념으로 생각을 해요. 그러니까 베이시스라는 게 무슨 소리냐면, yeah, so yeah, here's a question, which I think is really good question. So basically, in this case, eigenvector becomes your non-trivial solution from this homogeneous linear system, right? But in this case, usually the homogeneous linear, when the matrix B has a linearly dependent column, and suppose that B has one free variable, okay? And then if you recall about this parametric vector form, and then the solution for X coming from here will be something like this: C1, yeah, C1 times some vector 1, 2, 3, 4. So we obtain this kind of parametric vector form from the row operation, right? So that was what we obtained, and this was our non-trivial solution, right? And then it gives us infinitely many number of eigenvectors, right? Because it has so many vectors, right? But in this case, we consider only the basis, or yeah, essentially in the eigenvector and eigenvector relations, only the direction matters. I mean, the direction is the only part that is important, but the magnitude can be anything. So for example, so suppose some vector x, which was 1, 2, 3, was satisfying this guy. Okay, but it's x. But x being 2, let's see, 3, 6, 9, which is 3 times more than the original vector. Even if we plug this vector into this eigenvalue vector equation, it will be still true, right? So how can we prove that? So let's see. So x prime is x3, and then suppose x was satisfying this, and then what if this, yeah, so what about this equation? Ax prime is 8 times this guy, and 3 times ax becomes, yeah, so let's make it 2 because it's coinciding with this guy. So it's 2, and then we factored out 2, and then 2 times, what was ax? Ax was 3 times x, right? And then 3 times 2x, and this guy is 3 times x prime, right? So once you find one eigenvector, even if you stretch out that eigenvector to some degree, for example, like 2 times larger in terms of the length, but still the direction is the same. If the direction is the same, and then that will become also your eigenvector, right? So in this case, when talking about the number of eigenvectors, so as I mentioned, if the matrix size is 4 by 4, for example, 4 by 4 matrix will only have like 4 eigenvectors at most. So the maximum number of eigenvectors that we have can be only 4. Okay, so when talking about this really small number of eigenvectors, we only talk about the basis or the direction vector. So here in this case, this is our direction vector obtained from this non-trivial, this homogeneous linear system, right? So from there, if we had only one free variable, and then we will have this one basis vector for our solution set, and then this direction vector will be just one eigenvector that we have. Okay, so so some other vectors that are along this line or the span of this guy, I mean that they are all considered to be contained in this one eigenvector. Okay, so that's how we count the number of, that's we count the number of distinct eigenvectors. Okay. So again, the direction, I mean only the direction matters. So if the direction is the same, we consider them as just a single eigenvector. Okay, so okay, so back to the slide. So we are solving this equation, and then vector x or eigenvector that we obtain from here is actually also called the null space, right? So what was the null space? Null space was something like this. So all the possible solutions satisfying this homogeneous linear system. So our eigenvector is belonging to this null space of this matrix A minus lambda I. Okay. Okay, then let me mention one more thing here. So that will be that will be what we will learn in the next chapter in 5.2 I think. So in this case, as I mentioned, your matrix A was kind of invariable. I mean, so A can be invariable or not invariable, but it doesn't matter because we have a freedom. We have a freedom. I mean, we can choose whatever value for this lambda or this eigenvalue. So we can choose whatever value for this eigenvalue so that this matrix A minus lambda I becomes non-invariable, right? So this one has to have linearly dependent columns, and thus they should be non-invariable. And then, how can we find this lambda? So when is our matrix non-invariable? That was determined by this determinant, right? So if A was non-invariable, then the determinant of it was 0, right? So in order to solve, or in order to obtain this lambda value, we actually solve this equation. Determinant of A minus lambda I should be 0. Okay, so that's how we make this A minus lambda I non-invariable. So those eigenvalues are obtained by solving this equation. Okay, and then regardless of the size of this matrix, so this one should be of course square matrix. The determinant is only defined in the square matrix, and then whatever size of the matrix that we have, its determinant is only the scalar, right? So determinant is a scalar, right? After just multiplying all the things, and then the resulting determinant is always the scalar. So this is just a scalar. So this part is a scalar, and this 0 is essentially a scalar. It's not a vector or something like that. Okay. So this one gives us some polynomial equation. So polynomial equation means, we will see the example from the slide as well. But suppose our matrix was 1, 2, 3, 4, 5, 6, and 0, 0, 0. So suppose we are given this special upper triangular matrix. Okay, and then what is A minus lambda I? That is minus lambda, minus lambda, minus lambda, right? And then what is the determinant of this guy? 대각선에? 네. So the determinant of this guy, especially when your matrix is upper triangular. And then it will become just the product of the diagonal entries. So it will become 1 minus lambda, 2 minus lambda, and 3 minus lambda. And it should be non-invertible, and it should be 0, right? And then this guy is third order polynomial. So it means like a so it has minus lambda to the power of 3 and some lambda squared and some lambda and some constant becomes 0. Okay? So that way we can see that in the case of 3 by 3 matrix, this guy will be just a polynomial with the degree of 3 for this lambda. Okay? And then we have to solve this equation. And then in this special case, okay, so before subtracting lambda, this upper triangular matrix was it invertible or not invertible? So what was the determinant of the original matrix? 6. 6 is not 0, so it's invertible. So originally your matrix was invertible, right? But if you subtract lambda from the diagonal, and then we can definitely make it non-invertible, and that values obtained from solving this equation. And then from here, even before we just evaluate this product, this simple form will directly give us the solution, right? So what is the solution? 1, 2, 3, right? 1, 2, 3. So 1, 2, 3 are your eigenvalues for the matrix that we are given here. Okay? But yeah, in this special form of upper triangular, it was kind of easy. But what about this? 1, 2, 3, 4, 5, 6. Okay, I change it this way. It's not an important part. But here, suppose our matrix A is this form, which is just a general matrix. And minus lambda, and minus lambda, and minus lambda. And then we have to write this guy, determinant of A minus lambda I, and that should be 0, right? And then it will be also some kind of third order polynomial in terms of a lambda. So once you obtain this, and then you will have some lambda cubed, and lambda squared, and lambda and some constant being equal to 0. Okay, you will get this kind of equation. Okay, and that equation is called characteristic polynomial, in Korean, what's the polynomial? In Korean, what's the polynomial? 다항식이 polynomial이죠. 다항식. So equals 0 is the equation because we are equating the two things. They are equal, right? But in the case of polynomial, which is 다항식, it's just this expression. So it's a third order polynomial, which means 3차 다항식이 돼요. 네. 그다음에 we solve this equation, making this third order polynomial becoming 0, and then we obtain eigenvalues from this equation. And then this polynomial is called characteristic polynomial, and this equals 0 is called characteristic equation. And characteristic means, so characterize, or your character means some kind of your personality, right? Or your distinct kind of traits, or 특성이 characteristic이죠. So this equation is actually giving you some kind of characteristic. It tells you some information about the characteristic of your matrix A. So that's why we call that as characteristic equation or characteristic polynomial. Okay, okay, and then let's. So let's get back to this simpler example. where we obtained lambda as 1, 2, 3. Okay, and then we obtained eigenvalues here, and then the next step is to obtain eigenvectors, right? So for each of the eigenvalues, so suppose eigenvalue was 1, and then we can form this a minus lambda I. 1 minus 1, 0, 1, 2, because we are subtracting 1 along the diagonal, 4, 5, 6, 0, 0, 0, right? And then how can we obtain the eigenvector? We solve this guy, a minus lambda I, and x becomes 0. So this is our a minus lambda I when lambda was 1, and then we set x here in 0, and then we just perform the row operation on here. So this is just a typical kind of a way of solving a non-trivial solution, or this homogeneous linear system. And then we obtain the parametric vector form, and that basis, or the vector determining the direction, becomes your eigenvector. And that eigenvector, suppose that eigenvector was 1, 2, 3. And then this lambda 1 becomes 1, and v1 or x1 or v1, which was an eigenvector. This kind of pair is one kind of pair that we obtained for eigenvector and eigenvalue. Okay, and then we can do the same thing for lambda equals 2, lambda equals 3. Right? So that's how we obtain this eigenvalues and eigenvectors. That's it for today. Yeah, thank you very much, and yeah, let's meet next time.